Have you ever wondered what actually stops someone from snooping through your files on a shared computer? In the world of Linux, which runs pretty much everything these days, from giant servers to your smartphone, that stuff is not left to chance. It's actually a really carefully designed system, and today we're going to break down exactly how it all works.
So let's start with the big question. If you have a system with lots of people on it, how in the world do you control who can do what? It doesn't matter if it's a massive corporate server or just a computer you share with your family. You've got to have rules. We're going to explore how Linux builds its entire security model right from the ground up, starting with the absolute basics. We're going to tackle this in 4 main parts. First up, the who. We'll figure out who is on the system, which means users and groups. Then we'll look at the what. What are they allowed to do? That's all about permissions. Next, we'll cover the how. How do you get more power when you actually need it? And finally, we'll wrap up with the proof. How does a system know you are who you say you are? Okay, let's start at the very foundation, the who. See, before you can make any rules, the system first has to know who it's dealing with. So in Linux, the most fundamental, the most basic unit of identity is the user. Every single thing that happens on the system, every file that's created, every program that's run, it's all tied to a specific user account. Each account gets its own unique number, a user ID or UID, which is basically its digital ID card. This right here is the cornerstone of the whole security model. So how does the system keep track of all this? Well, it uses a file that's kind of like a public phone book, and it's called /etc/password. Each line in this file is like a profile for a single user. It's got their login name, their unique user ID, where their personal home folder is, and even what program starts up when they log in. But notice that little X in the password field? That is a huge security detail, and trust me, we will circle back to that one. So how do you actually get a new user on the system? Well, thankfully, you are not expected to go in and edit that complicated file by hand. No. Instead, an administrator uses a really simple command like add user. It just walks you through the process, asks for stuff like a password, and then bam, it automatically creates the user's account, their private home folder, and takes care of all the paperwork. It's a much safer, automated way to do things that prevents a lot of headaches. Now, imagine trying to manage permissions for hundreds of users one by one. It would be a total nightmare. And that's where groups come in to save the day. A group is just what it sounds like, a collection of users. But it's a really powerful concept. Instead of giving 20 people individual keys to a project folder, you just create a project group, put all 20 people in it, and give the key to the group itself. So much more efficient. Okay, so we've established who is on the system. We have our users and our groups. Now we need to define what they can actually do. And this brings us to permissions and access, basically setting the rules of the road. In Linux, it all boils down to 3 basic permissions: read, write, and execute. But here's the really clever part. Their meaning changes depending on whether you're talking about a file or a directory. For a file, read is simple. You can see what's inside. Write means you can change it, and execute means you can run it like a program. But for a directory, read lets you list what's inside. Write lets you create or delete files in it, and execute is the one that trips people up. It means you can actually enter the directory. And this is how you see it all in action. You've probably seen that cryptic string of letters when you run a command like ls-l, and it can look pretty intimidating, but I promise it's way simpler than it looks. It's just broken into 3 little sets of permissions. One for the file's owner, one for the file's group, and one for everybody else. So in this example here, the owner can read and write the file. The group can only read it, and everyone else, they can only read it too. That's it. But what if that owner group other model just isn't specific enough for you? What if you want to give Bob from accounting access to a file, but not the rest of the accounting group? Well, for that, Linux has a more advanced system called File Access Control Lists, or ACLs. They work right alongside the traditional permissions and let you create super specific rules for individual users or groups. It gives you incredibly fine-grained control when you need it. So, we have our users and we have our rules. But what happens when a normal user needs to do something that requires a bit more power, like, say, installing new software? This brings us to our next layer, the how. How can someone gain power safely? The answer is one of the most famous commands in all of Linux, sudo. It's short for super user do. And here's the key. It doesn't give you permanent power.
Instead, it lets an authorized user run a single command with the full authority of the system administrator, or root. It's a safe, temporary, and logged way to do administrative tasks without giving away the keys to the kingdom.
So why all the hassle? Why not just log in as the all-powerful root user and be done with it? Well, there's a really good reason that modern systems disable root login by default. It's because running every single command with absolute power makes it dangerously easy to make a catastrophic, system-destroying mistake. One little typo, and your entire system could be toast. Sudo forces you to stop and think before you do something that powerful.
But, even sudo can feel like using a sledgehammer to crack a nut sometimes. So, in recent years, an even more fine-grained approach has gotten popular: Linux capabilities. The whole idea here is to take that giant all-or-nothing power of root and smash it into dozens of smaller, individual privileges that you can give directly to a program itself, not just to a user. Let's make that a little more concrete. Instead of giving a program full root access, you can give it just one specific superpower. For instance, you could give it the ability to change who owns a file, but nothing else, or the power to create special network packets, but without being able to touch the file system at all. You give a program only the exact privilege it needs to do its job, and absolutely nothing more.
A perfect, simple example is the ping command. You use it to check if another computer is online. To do that, it needs to create a special kind of network packet, and that's a privileged operation. In the old days, a program like this might have needed full root power, but now it's just given that one single capability for networking, and that's it. It's a way more secure approach.
A more complex example is a tool like Wireshark. It needs to capture all the traffic on your network, a highly privileged task. But you definitely don't want that entire complex graphical interface running with all that power. So the system is split. The user interface that you click on runs as a totally normal user, but the little back-end engine that does the actual capturing, a program called dumpcap, is given just the special capabilities it needs to talk to the network hardware. It's a really brilliant separation of power.
Okay, we have our users, our rules, and a system for granting power when needed. But this all hinges on one final absolutely critical piece of the puzzle: the proof. How does the system know you are who you say you are? This is all about authentication.
And authentication is typically based on three classic factors you've probably heard of. First, there's something you know, like a password or a PIN. Then there's something you have, like a physical security key or a badge. And finally, there's something you are, your biometrics, like a fingerprint or a face scan. The really strong systems will combine at least two of these. All right, remember way back at the beginning, we looked at that Etsy password file and saw that weird X where the password should be? Well, now we can finally talk about why. It's a critical security feature. That password file is publicly readable, so anyone can see the list of users. The actual encrypted passwords are kept in a totally separate, highly restricted file called Etsy Shadow, and only the root user can even look at it. This separation is absolutely vital for security. But just encrypting the password isn't quite enough. To stop certain kinds of attacks, the system uses something called a salt. Before your password gets encrypted and stored, the system adds a unique random string of data to it. That's the salt. What this does is ensure that even if two people on the system pick the exact same password, like password123, their encrypted versions in that secure shadow file will look completely different. It makes cracking them way harder. So, we've journeyed all the way from the simple user account to the fine-grained control of capabilities. We've covered the who, the what, the how, and the proof. But this whole evolution leaves us with a really fascinating question to think about. If the all-powerful root privilege can be broken down into dozens of these tiny, distinct capabilities, what does ultimate power on a system even mean anymore? The very definition of control is changing. Something to chew on. Thanks for joining me.